Okay, so our next topic is reversible adiabatic process. Now, what is an adiabatic process? An adiabatic process is defined quantitatively by two things. First thing is the heat added or subtracted to the system is zero. This is only possible if the process is very fast. Right? And during this process, neither pressure, volume, and temperature are constants. The PVT are not constants. So all of these variables actually vary during a reversible adiabatic process, in an adiabatic process. So internal energy is not just a function of temperature here, because P and V varies if temperature also varies. So you don't have you cannot only express internal energy in terms of temperature, because you have the other variables which can vary independently. That is most important. It can vary independently. So if you have to fix two of the variables to get one fixed. Anyway, so we will derive the relevant equations for an adiabatic process. So how we do that? Let's start with the diagram. Keep in mind that del Q is 0. This is very important. So no heat is added or subtracted to the system while an adiabatic process is on. So let's see what an adiabatic process. Consider that these are the isothermal lines or the isotherms. Okay. So along this, the temperatures are constant. Suppose I want to jump from here to here. Okay. So this is T1 and this is for T2. I want to jump here to here. So this is what an adiabatic process looks like. So we have a different temperature, a different pressure and different volume at this point from this one. So how do we consider this? Let's say, so ultimately what we need to do, ultimately whatever comes, you have to substitute in the first law of thermodynamics. That is the idea. That is du is equal to del Q minus del W. So what you need to actually compute is del Q and del W and du and find a relevant expression in terms of pressure, volume and temperature. Because these are the measurable quantity. Always remember that whenever we want to measure any quantity, that has to be expressed in terms of pressure, volume and temperature. So these equations need to be substituted with P, V and T. So let's see how we do that. To do that, let's say I will just delete this part and just write remember, it doesn't fall in any isotherm. Okay. This is T1, this is T2. This is say U1, U2 and U3. So to consider, to derive the relevant equation, I have 3 points, 1, 2 and 3. So if I need to write the relevant equation for this one, so du is what? Du is U3 minus U1. Internal energy is a state function, as I have already told. So U3 minus U1 is your change in internal energy, this point and this point. So that can be also written as U3 minus U2 plus U2 minus U1. It can be written in this form, right? Now let's write individual first law equations for this and this. U3 minus U2. How do you write U3 minus U2? Look at this picture. This is very important. U3 minus U2 here. Along this line, there is no variation in pressure. Pressure is in the y-axis and it is constant. So only your volume is varying. So if you write del U from 2 to 3, we'll just write it as del U 2 to 3 plus del U 1 to 2. Always put this mark that shows you a reversible equations. To del 2 to 3. Del for the state 2 to 3, the first law of thermodynamics can be written. It's already mentioned that this is an adiabatic process. So del Q is 0 for this system. So it's basically a constant pressure system. So your equation becomes PdV. Right? This is the equation. So del U to 3 can be written as PdV. Okay? And del Q is 0. Now what about from 1 to 2? What about this? For del U 1 to 2, see, here the volume is constant. So if it's a volume is constant, there is no work done because P del V is 0. Right? And you also don't know how to measure the Q. So internal energy has to be expressed in different way. How do we express that? How do we express that? Just recall something. Just recall something. We have mentioned that del U, del T at constant volume is your CV, right? For this process, so du can be written as CV dt, right? Because there is no way I can find the work done, because the work done here is basically V del P here. So we don't have an expression, relevant expression to substitute for that. Q is always 0 here as well. So we have to do it with the help of heat capacity equation. du is CV dt. So if we substitute that, it becomes del U1 to 2 is CV dt. It's very important. Okay.